Okay, I'm going to go over the first page of the practice test. Hopefully you got a chance to look at these on your own and think about them. I don't want to just do them all for you and not before you get a chance to think about them, but that's what I'm going to do because I want to make sure that you know how to do them and have the right answers. So, okay, let's get started. So, tangential speed at the outer rim of Malia's Ferris wheel is 30 and the angular velocity is 2. What's the tangential speed at position 1/3 of the way to the center? So omega is how many radians per second. That's how fast it's turning. No matter where you are, that's the same. Omega stays the same. Tangential speed is how fast you're actually going, like tangent to the circle. And that is the velocity is omega times r. So it goes linearly as r. Omega is the same everywhere in the circle, right? The same, no matter where you are in a circle, it's always spinning the same number of times per second. But your velocity goes as radius. So if your velocity is 30 on the outside, if you're 1/3 of the way to the center, okay, that's tricky. That means you're 2/3 of the way to the outside, 1/3 less. If you're 1/3 less, or you have 2/3 of your original, then you have, so 2/3 of 30, and I made the math easy, is 20. So it would be 20 meters per second if you're going 1/3 of the distance. And then, what's the angular velocity if you're 1/3 of the way? Oh, what is the angular velocity 1/3 of the way to the center? That doesn't change, right? So omega is the angular velocity, and that's just a trick question. It's the same, doesn't matter. You're still going the same number of circles per second, but a smaller radius, you're not going as fast. Okay, so that one is just kind of understanding the concepts. Okay, number 2, we have a rotating space habitat, 100 meters from the center, it's rotational acceleration, which means centripetal acceleration. So rotational acceleration is like centripetal acceleration is v squared over r. We want to know what it is then when you go 70 meters from the center of the habitat. So that's what it is at 100, it's 20. So what is it when you go 70? Okay, now first off, two things change. The radius changes, but how fast you're going changes too. So we need to plug in for our v squared there to get a radius out of that. So when you're going in a circle, your velocity is 2 pi r. You go one circle. 2 pi r is a circle, right? The circumference of a circle and the time for one circle, whatever that is. We could figure that out, but it doesn't really matter. That's your velocity. Circumference divided by the time for a circle. Now, what's v squared? So now we just squared that. V squared is to square everything, 4 pi squared r squared divided by t squared. Now let's plug that into the formula. So then we go AC is v squared over r, which is now this, 4 pi squared r squared divided by t squared over r, or times 1 over r. The r and the r squareds cancel out. So we're left with 4 pi squared r divided by t squared. Okay, t is the same no matter where you are in the circle, right? The time it takes to go in a circle, just like the omega, time it takes to go in a circle is the same. So basically the centripetal acceleration varies with r. If it's a certain number at 100, it's going to be 70/100ths of that if you go 70 meters in. So the new centripetal acceleration then, our new centripetal acceleration will be 70/100ths times 20, because again it varies as r. So if you go 70 of the way in, it's now 70 of what it was. 70 of what it was is 100. So 70/100ths of 20, let's see, that's 1400 divided by 100, so that'd be 14. So it'd be 14 meters per second squared. The important part there is it varies as the radius. All right, let's look at number 3. So the torque is 80. So he triples the lever arm. Same force, what's the resulting torque? So torque is often written with this little, the letter tau like that, not normal t, because normal t is like the period, how long it takes to go in a circle or something. So you have this little funny t, the Greek letter tau, and it's equal to the radius times the force, and that's as long as the force is at a 90-degree angle. So really, it's the force times the sine of the angle you apply it at. So like if this is if we're turning our handle here, we're applying a force here, this is the angle. So you want it to be 90 degrees because sine of 90 degrees is 1. But anyway, if everything's the same, if that angle stays the same, doesn't matter. If you triple the lever arm, that means R is 3 times bigger. Your torque is 3 times bigger. So this is easy. It's just 3 times 80 Newton meters, which of course is 240 Newton meters. So that's why you want a long handle to make you that much stronger in a sense. It's kind of like mechanical advantage. The longer the handle makes you stronger. Okay, number 4. This is a classic seesaw problem. So you draw the seesaw, let's see, 2 meters. So let's say Serena is over here. So here's Serena, and that's 35 kilograms. And you want to know what distance should Callan sit if Callan is 50 kilograms. So Callan does not have to sit as far away, because in this case we say Callan has more mass. So my picture should more look like this. So 50 kilograms. And this distance here is 2 meters, and we want to find the distance that Callan is, right? It's 2 meters from the fulcrum. The fulcrum usually draws a triangle. That's like the pivot point. Fulcrum is like the pivot. So in these equations, it's the torque. The torque is a lever arm times the weight. The weight's going straight down. Weight's going straight down, so it's 90 degrees. So it's distance times force equals distance times force. Now the forces both have a g in it. The force is mg, right? The force of gravity. But since they both have a g, they're going to cancel. So all that matters is the mass. So we don't have to. You can put the g in, they're just going to cancel. So what we do is we just say, okay, 35 times 2 is equal to 50x. And again, we can put a g here and a g here and they'll cancel. Or the distance we want is just, what's that, 70 divided by 50, which is 7/5, which is 1 2/5, which is 1.4. So 1.4 meters. Okay, so the point here is force times distance equals force times distance to balance. All right, so this is just a centripetal force problem. 200-gram ball at the end of a 2-meter rope makes 3 rotations per second. With what force must be pulling in on the string? So, okay, the centripetal force is mv squared over r. So we know r is 2, but we don't know the velocity. So that's one thing we got to figure out. And we got to be careful. I said 200 grams. We always want kilograms. So this is just we got to make sure we put 0.2 grams. Okay, so remember that 200 grams is 0.2 kilograms. Sorry, 0.2 kilograms. Okay, so let's see. So we need to figure out the velocity. So if you're going in a circle, your velocity is omega r. That only works if we're using radians for omega. Okay, so we know the radius is 2, so we need to get omega in radians. So we have 3 rotations per second. That's omega. Omega is equal to 3 rotations per second. We want radians, but one rotation, one circle is 2 pi radians. That's the whole idea. A circle is 2 pi radians. So that's 3 times 2 pi radians per second, which is just 6 pi. 6 pi radians per second. So V is omega r, which is 6 pi times 2, and it's per second here, and our r is in meters, so everything is right. So that's what, 12 pi? So 12 pi meters per second. So this number then becomes mass is 0.2 kilograms times V, which is 12 pi meters per second, and that's squared. And then we divide by the radius, which is 2. And now we plug it all into your calculator and get some crazy answer. Don't forget to square the 12 pi, so that's 144 times. And I get times 0.2 divided by 2. I get 142. You might want to check that, but I get 142 since our units are kilograms and meters and seconds and everything. Make sure everything's the same units. We know that we're going to get newtons. So 142 newtons. That's what I think the answer is. All right. Number 6. Quinn rolls an empty can, a broth can, and a pumpkin can down an incline, all the same size. Which will win? Okay, this all has to do with the idea of rotational inertia, which you should have read about in the book. If you didn't, go read that again. All about rotational inertia. How hard is it to spin something? And here is the idea. The more, let's say we're spinning a big hoop like this, like a bicycle wheel, and let's say it's a really heavy bicycle wheel, it's all lead around the outside. That's going to be really hard to spin because all the mass is as far away from the center as possible. So you're moving a lot of mass because it's away from the center. Let's say we had a little wheel that weighs the same amount, but now the mass is close to the center and it's easier to turn. It doesn't have to go as far to go in a circle. If you're trying to push the big wheel, you got to make it go really far. While the little wheel, you can make it go faster because it's not as far from the center. So the point is the more the mass is away from the center, the harder it is to move. It takes more, it's got more inertia in a sense because it's got to move in a bigger circle. So what we look at then with these cans is, again, let's look at how the cans work. So an empty can is like this. It's empty. All the mass, now it doesn't weigh much, but all the mass is far from the center. A broth can, like water in the inside, and a pumpkin can, let's say they weigh exactly the same, which they pretty much do. But in the broth can, if you roll like an empty thing of liquid water, the water won't really turn in the middle because there's not much friction. The can spins and the water doesn't spin. So you don't have to turn the water. So it's actually really, really easy to turn because all you're turning is the can. Now here's the point. Gravity is pulling this thing down. So gravity pulls on the mass. So these have the same force pulling down, the same force of gravity pulling down, but the broth can, the gravity doesn't have to spin the broth. Here the pumpkins stick. If you roll a pumpkin can down, you're spinning the pumpkin inside. So gravity, the same gravity now has to turn a lot of pumpkin. Doesn't have to turn a lot of broth. And here, empty can doesn't weigh much, so way less force of gravity. So the mass doesn't matter. Okay, the point is gravity depends on mass and turning depends on mass. Mass doesn't matter since an empty can is all distributed as far away from the outside as possible. It's the hardest to turn. So the point is the one that's easiest to turn wins. Big force of gravity, small turning going on here. So the broth can will win. So the broth can win. I do this in class. Unfortunately, we couldn't do this in class for obvious reasons, so hopefully that makes sense to you. And then second is the pumpkin. And then third is the empty can because of the distribution of the mass in the can. And again, read the section on rotational inertia. Hopefully that will help explain it. Now I expect you to write an explanation here. I just said the answers, but try to explain what I said in words and read in the book how that says. Hopefully it makes sense. Okay, now a large marble and a small metal ball down an incline, which will win? They're both spheres. They're both solid. Again, mass doesn't matter because a large marble, whatever it weighs, small metal ball, whatever it weighs, the more gravity, the more it pulls down. And so it turns out it'll be a tie because they're the same mass distribution. The mass is solid throughout the whole thing. And the mass doesn't matter because gravity pulls harder if it's more mass. Now, there's air resistance, like a ping pong ball might have a lot of air resistance. But, okay, first, a ping pong ball is empty on the inside. So even if there's no air resistance, a ping pong ball will roll slower because it's hollow. Just like the wheel, all the mass is as far away as possible. So if you have a hollow ball, it's going to roll slower than a solid ball. Okay, last one here. How does Super Sage use angular momentum? I should say it's a tie. Yeah, I said a tie. Explain how Super Sage could use angular momentum to make the Earth stop rotating. Okay, so the Earth has angular momentum, right? It's rotating along at the equator. It's going pretty fast, by 1,000 miles an hour at the equator. And if you want to make it stop, you have to go the same way. People always want to think the opposite way. If you go the opposite way, how do you go fast this way? You push it backwards the other way. Okay? There's two ways to look at this problem. You can look at it as Newton's third law. If you walk this way, to walk this way, you push the other way and you're making it go faster. So all you gotta do is go fast enough this way so you push it. Well, actually, then you can make it go as fast as you want. But let's say you're going the opposite way, or the same way the Earth spins. How do you do that? By pushing backwards, which is opposite direction Earth is moving, so you're going to slow the Earth down. So all you got to do is run fast enough in the same direction to slow it down. Now the other way to look at it is to using angular momentum. If you're on the Earth, you're with the Earth, you're not an outside force, there's a total angular momentum is conserved. So the idea is that total angular momentum, the spinningness of the object, can't change if you're a part of it. Only if a giant can come in and stop the Earth from spinning. But if you're a part of this system and it's all vacuum around it, there's no friction or anything, you can't change the total angular momentum. And they say that is conserved. You can't change it. But what you can do is steal it from the Earth. So the Earth has a lot of angular momentum because it's spinning. So you need to take it by spinning really, really fast in the same direction. So now you have the angular momentum and the Earth has none left. So to make the Earth slow down, and it's the same idea, you got to go in the same direction so that you have the angular momentum. Now obviously the Earth is way heavier than you, so you're going to have to go way, way, way faster. Your speed will be the speed of the Earth, which, like at the equator, is 1,000 miles an hour, times the mass of the Earth divided by your mass of you. Mass of the Earth is way bigger, so you'd have to go way faster than the speed of light. Okay, it's not going to happen, but that's why it's Super Sage. Super Sage can do anything. So realistically, you're right, it's not going to happen. But that's the idea. If you take all the Earth's angular momentum, which means you got to go have all the momentum of the Earth, then the Earth would stop because you have it all because you're going so fast. Okay, hope that all makes sense. I'll continue with more videos on the other ones later. Thanks for listening. Bye.